Good afternoon, everyone. Okay, you all can hear me. Okay, great. So, good afternoon, everyone. It's great to be here. The weather out is very good. I just drove here from Seoul, and it's a beautiful drive out here. So, very nice to be here today. So, myself, I'm Chetan Hiremath. I work at Intel as a principal engineer based in Portland, Oregon. My current role is looking at architecture for 5G, focusing on the core network aspects. And today we'll talk about some of the evolutions of 5G and what does it mean from an architecture standpoint. If you want to deploy this kind of a capability, it's a big disruptor, and we'll briefly talk about what are some of the opportunities, what are the challenges, and what are the kind of things that we can go make happen using SDN NFV technologies, and why it is important as a key enabler for 5G technology in particular. So quickly, some of the context background. What is happening from a technology standpoint is there are a lot of new type of devices that are going to be brought into the network. So far, when we look at 3G and LTE, predominantly it had been mobile broadband or smartphones. People use the smartphone for either voice calls or video calls or things like streaming and things like that. But there's only so much amount of additional capability that that kind of a network can provide. And along with that, there are new type of devices that are going to be coming online. Some of the data that we have seen within Intel tells us that the amount of sensors that might come on a network that will communicate is in the order of billions. It's not in the even order of it's a pretty big number to even comprehend. And if you want to just compare and contrast, the world population today is how much? Anybody can take a guess? Very close, about 7.5 billion. That's the population of the world today. Okay, and some of the analysis that we have seems to indicate the amount of sensors that will be coming online is in the order of hundreds of billions of sensors. And while all of these classes of devices may not be the same, they may not have the same type of behavior, same characteristics, but they all have one thing in common. They will want to communicate. They want to send some information or receive some type of information. And what is required is a network that can handle those diverse type of communication that these type of devices may want to do. And many of these connections, as we see here, these are all going to be machine to machine, which means that they are not going to be communicating to humans as with all of the communications that we've seen mostly so far. So these communication will be between machine to machines, which means that there is no human involved in between. Those devices are going to be completely capable of interacting within themselves to do the work that they need to do. A classic example nowadays we see is, I think in the previous video, Mr. Park showed vehicle to vehicle. That's a machine-to-machine type of a communication, right? I mean, they can communicate between each other. They have computing capability. They can run the algorithm. They can determine what action to take, when, and how. So that's a very classic example. And another piece of data that is very critical or it's a good eye-opener for us at least is how much amount of data is transferred for these type of machines that are going to come online, or even for the type of data transfers that we as humans are going to do, right? So some of these numbers that we collected was startling. Internet users may end up consuming about 1.5 gigabytes a day. Just a few years back, my mobile subscription at a monthly level was a gigabyte, right? So that's a big difference that we see. And even machines, for example, if you take aircrafts or cars, the amount of data that gets transferred is extremely large. Even if you take just the internet users itself, right, mobile traffic, we already have data that tells us that mobile data is, on a daily basis can go in the order of about 20 to 25 petabytes per day. That is 20 to 25 petabytes per day on one network. So that just gives a perspective about where things are going. So if you take a confluence of few different things that are happening here, the data traffic for the mobile broadband is itself increasing significantly, and it continues to increase. The type and the different categories of devices that will come online, they will want to communicate, that is going to increase over time. And the type of devices that will come online and will communicate, there are few of them that we can think of, but pretty sure there are many classes of devices that we haven't even thought about today. We simply don't know everything about what's going to happen. But what we do know is there is going to be this explosion of devices that will come online. And we need a network that can comprehend the different classes of devices, different types of communication that will happen further down the road, and start to prepare for that. And that is what 5G is. So the challenges, three vectors quickly, right? If we broadly speaking, one is if you want a network that can scale to the kind of devices, the kind of data traffics that we just briefly touched upon, we are talking about a network that is vastly different in scale and complexity than the kind of networks that we know of today. You know, if you have a device that may want to transfer data, say every hour, for example, you may have devices that may want to transfer very small amount of data once a day. Or there may be devices that will continuously keep transferring data, communicate between other devices, and they may need very high bandwidth in some cases. In some cases, they may need extremely low latency. For example, if there's a robot on a factory floor and it needs to interact and coordinate activities with other robots on the factory floor, it gives a pause for us to think what kind of algorithms are required to run such kind of an equipment, what kind of communication that they might need to do to interact and coordinate between themselves. And that gives a perspective of the kind of low latency that it will need to be able to react to the kind of work that they need to do. So the scale and scope is a big challenge compared to what we've done so far, what the industry and what the world has done so far in terms of network. So that's one big challenge from itself. The scale itself is vastly different and pretty big. Then second aspect is the bandwidth itself. The amount of data transfers that are required for these different classes of devices is very different. Some of them are very small amount of data transfers, but the number of those classes of devices are going to be extremely large. So that itself presents a different challenge and a different problem space versus having relatively smaller number of devices, but each of those devices send large amount of data. Both of them taken together, yes, the amount of data transferred is very large, but the characteristic of the data transfer is very different, and it poses a very different challenge to the network itself, both from a device, the network, and the applications itself. And when we talk about the network, I'm not talking purely about the core network here. I'm talking about the entire network, whether we talk about the access, whether you talk about the transport, whether you talk about the core. 5G is going to touch every aspect of the network, and that itself is part of the challenge. And lastly, the latency itself. You know, we just talked about the different classes of devices and, you know, the kind of low latency that it requires. And in the video that Mr. Park showed earlier about the cars going around in a track and reacting to the situations on the track, the kind of latency that it needs is very small because it's a moving car. I mean, I was just thinking about when I was looking at the video. It's a moving car. And the distance between the cars is relatively small. I saw it was like something like 20 feet or something. And if you try to compute the speed at which the car is moving and the distance between the car is only about 15, 20 feet, if you back calculate from there, we can guess how much reaction time is there for the car following the first one to be able to react to the kind of actions the first car takes. You know, it's in the order of microseconds, hundreds of microseconds, tens of microseconds. So when you look at that, and then you try to think, there's some sensor on the car, it has to sense some sort of information, feed that information back into the computing capability in the car, and run an algorithm, and then determine what action to take. And to do all of that, and then take that action within that stipulated time, you need a capability that can communicate all of the sorts of information at a very, very low latency. So that poses another challenge for this kind of a new network that is going to get deployed. And another aspect that we see here is any device that communicates will also compute. And any device that computes will also want to communicate. So historically what we have seen is compute and communication have been completely separate, independent entities by themselves. That is no longer the case going forward. A computing device communicates and a communication device also computes. So it's a confluence, or it's a mix of what previously used to be completely separate domains. And that is one very critical aspect of what devices on 5G are going to go enable for the ecosystem. So essentially, when we look at something like this, the scale of this network is completely end-to-end. All the way from the devices itself. It's the classes of devices that we know of today, the new classes of devices that are going to come, the new type of usages that those devices may want to deliver end-to-end. That's a completely new category itself. And to do something like that, we need a new type of a wireless air interface protocol, wireless capabilities, whether we talk about millimeter wave technologies, where we go into whether the 28 gigahertz band or 60 gigahertz band, 30 plus gigahertz bands. And to be able to transfer data on such kind of an interfaces, you need a protocol that can comprehend how to do the data transfers, how do you transmit signals at those frequencies, how do you handle the interference, how far can you take the radio waves, how far can you transmit, how do you handle noise on the air interface, how do you detect that noise, remove the noise from the signal. That itself is a completely unique and a different challenge by itself. Then the access network itself are going to be very different. Now we think about an access network where it needs to be able to cater to a few millions of devices that will send data very infrequently, as opposed to something like a mobile broadband where many people they want to transfer data, but the size of the data transfers typically tend to be in the medium to large chunks. So the access networks itself are going to be required to comprehend these different varying needs, and it's not going to be an one size fits all from an end solution standpoint. We may have to look at how do we cater to these needs in a unique fashion, and along with that, how do you have a network that can comprehend these amount of data transfers, these amount of different classes of services that these kind of devices may need. And then in the back end, we obviously have the cloud where you have all of your application servers, and that's where all the data goes. Data gets processed by these devices that are sent by these devices. So what we really see is 5G is going to impact everything, right from the devices all the way back into the cloud. Everything is on the table. It's part of the scope of where the implications are and where the innovations are going to require to be happen. And essentially, this is where we look at as a key enabler for 5G. When we look at these devices, vast variety of classes of devices, and we have different classes of access technologies, whether we talk about LTE, 5G. We are looking at 5G, but we don't think LTE is going to go away anytime soon. So we are going to have those type of technologies, and then along with that, we are also going to have technologies, other radio access such as NB-IoT or CAT-M for IoT class of devices, and other technologies such as Wi-Fi, WiGig. They aren't going away. It's going to be around. Then you have the wired technology as well, and we all talk about wireless, but there is wired interfaces as well. Those are not going away either. So you have this vast variety of technologies from an access standpoint. And essentially what that means is we have a complete heterogeneity in type of connections. And when we look at the type of platforms that are required to go deliver solutions to address something like this, we see that we need a platform where it should enable innovation, it should enable open interfaces, open capabilities, open stacks, so that everybody should be able to create solutions, innovate on it, while at the same time provide basic infrastructural enabling. Like you need some basic ingredients on that platform. You need compute, you need networking for communications, you need storage, and then how do you mix and match these ingredients is something that needs to be determined at the time when you build the platform or at the time when you want to deliver the service. And we think that virtualization is going to be one of the critical enabler for 5G. And that allows us a way wherein you can create services, you can create network functions, and you can deploy applications or services or network functions independent of how the underlying platform is built. And you need to have certain capabilities such as the NFV capabilities wherein you can determine which service can be deployed where and how. And all of that process needs to get automated, which currently is all done relatively statically at this point in time. So SDN NFV, we think, does bring a lot of possibilities and potential and opportunities, but it also needs a lot of work to go deliver on that potential or deliver on that promise. So as I always tell our back in our team, with challenges comes opportunities. So they always go hand in hand. When you have a problem, there are opportunities to innovate, opportunities to come up with new solutions that somebody may not have thought about, and that creates an opportunity for innovation and a spiral for new categories or new sort of development on top of that. So essentially, where we think the infrastructure is headed, at least from our standpoint, where we see from at Intel is things are going to be based off virtualization, where the compute, the storage, the networking, those are all ingredients in a resource pool. Now, how do we mix and match is something that needs to be done as a part of configuring the platform. And then once you have configured the platform and configured your environment, then you can deploy services on it. And the orchestration software, we think, is a very critical component as a part of that. And to be able to do that in a telco environment where we need very high reliability, very high availability, where we typically talk in terms of 5 nines availability. The downtime is extremely small. What that means is we need some new metrics, new types of information to be able to determine whether a service can be deployed at a particular place reliably or not. And how do we do that? We do that by collecting different types of information. Instrumentation is extremely critical. Whether we talk about the performance, whether we talk about the utilization, whether we talk about where that particular service or the application needs to get deployed, we talk about how much power is being consumed. These are all capabilities that or information that we need to use in a more intelligent way to determine how these services need to get delivered. And the classes of services that we see are happening today, even right now, is something like virtual EPC or virtual network functions for mobile edge computing, or virtual RAN, for example. these are the type of virtual functions we see already being deployed, not only being tested, but also being deployed currently in the network. So we see that these types of virtual functions, these types of enabling is already happening in the industry. It has started to happen. So what that tells us is we are taking some steps to enable these kind of capabilities. Yes, maybe we are not there, we certainly are not there to the point where the automation is not there at the point today where somebody can say that, okay, I need to deploy a new network function for mobile edge computing. I go and click some buttons and the automation takes care of figuring out how, where that service can be deployed. You know, that's where we would want it to be, but we are probably not there yet. There's still not a lot of automation that needs to happen, a lot of intelligence that needs to be extracted from the system, and it need to be built into the intelligence to determine how those things need to be done. That's where these orchestration softwares become really important. And there's a lot of work happening in the industry, in the open source community along these lines, whether we talk about SDN NFV or OPNFV and different standards bodies. And there's a lot of good work happening, but at the same time, there is more that needs to happen. So one other capability as a part of this that we see is to enable something like 5G is something called as network slicing. And Mr. Park talked about it in his talk. Essentially, what has been traditionally a very vertically developed architecture or solution for 4G or LTE, we think that needs to get transformed into more like service-based or service delivery type of an architecture, where the network itself is sort of tailored to the kind of usages based on the type of service it delivers. Whether we talk about an IoT type of an usage or mobile broadband type of an usage. So we don't need the same set of capabilities for every service. For example, if we take IoT as an example, there are different classes of IoT devices. There are many classes of IoT devices that don't move around. Those are fixed devices, but they just happen to be communicating. So we don't need mobility for those classes of devices. So why build an vertical solution that has all of the capabilities for mobility for those classes of devices that don't even exhibit that behavior of mobility, right? So some of these devices may not even want to have their data go all the way back into the network because they may need very low latency, or maybe because that their boundary of operation is very limited. Maybe they don't need to communicate all the way back into the real cloud, so to speak. They may have local data, so they may cache all of their data locally, and the data is serviced locally. So mobile edge computing probably is one class of usages. So how do we tailor the overall capabilities of a network based on the class of device or the class of usage that those devices exhibit? So that is a problem that can be solved using a concept called network slicing. So you can build different slices based on the usage or based on the type of devices that will get connected to that particular slice. And you should be able to cater to those services or those slices differently. For example, we can have different set of functionalities in each slice. And within the functionality, you should be able to further have granularity of control of what feature set gets enabled, what feature set don't get enabled for those type of network slices. And these slices need to be able to be composed together dynamically. So that's again where the orchestration software also comes into picture, where you take the intelligence and you need to be able to configure your network such that you can create your network slices at runtime, and so that when the device is attached to the network, the devices can expose, okay, I am this class of a device, and they may expose some preference for, okay, this type of a network slice, and then the network decides which slice that particular device connects to, so that the device gets the kind of service it needs in a transparent fashion. But whereas in the network, there's a lot of things happening where the device itself doesn't know that it's connecting to slice A or slice B or slice C. As long as it gets the service that it needs, it's good enough. So essentially what that means is these the slices needs to be capable to be flexible in terms of its definition, in terms of how they need to be able to scale. They have various different processing requirements or requirements in terms of where those services need to get deployed. So these are the different diverse use cases or usage models in 5G, which can be deployed, can be built using NFV and SDN type of technologies. That's how we perceive things. And the more important thing is when you think about it, these open up an avenue for innovation, because if it's built on technologies open technologies such as SDN and NFV, which are basically inherently open technologies, it creates a situation where these type of capabilities can be defined or designed by a broader set of community in the ecosystem, rather than being developed something that is very vertical in nature. So it creates and spiral for innovation in the industry, and that is very important. And it's very important for 5G primarily because there are a lot of classes of devices, as I mentioned, that we know of. There are a lot of classes of devices or usage models that we may not know of today. And to be able to comprehend something like that, we need the broader industry to innovate on top of what inherent ingredients or capabilities that are available in the network itself. So within Intel, we are looking at a few different technology elements. We are looking at whether we talk about whether we talk about the air interface design itself. Intel is very active in 3GPP, in the analysis and definitions of these type of air interface designs. We're looking at things like, how do you define new types of process and package innovation that can cater to these type of technologies and requirements. Whether we talk about memory, silicon photonics, how do we connect these different nodes together? Where the amount of data that these things transfer, it's not copper connectivity, it needs optical connectivity. So silicon photonics is another area where we are working on next generation memory technologies. Within the baseband, Intel is working a lot on technologies such as massive MIMO, where we have either 32, 64, or 128-way antenna-based data transfers. We have working prototypes of split RAN signal processing. So you use a general-purpose platform, couple it with something like an FPGA, which is again a programmable element, and you build the software stack on top of it to do the entire baseband processing. We're working with the IEEE to define radio over Ethernet. So we have these cell phone towers or the RF antennas where the signals are received or transmitted from. How do you take all of that data coming over the RF interface and bring that data to a point where you can do the signal processing on it? So in IEEE, there is a definition of transferring radio data over Ethernet. So Intel worked with IEEE along these lines as well. The Intel is also looking at integrating some of the network IP itself, whether we talk about in the areas of baseband processing, acceleration, or for data plane for packet processing. Some of those capabilities Intel is investigating, working on, integrating as part of their product portfolios. Then using general purpose platforms, Intel has built FlexRAN, or what we call as a flexible RAN. So using a general purpose platform, use software to build the overall radio access solution. so that it becomes an platform ripe for innovation. We are showing how it can be built, how we can meet the overall timing requirements, the latency requirements. Similarly, we are also looking at how do we build the core network usages, whether we talk about the user plane functionalities of a core network. How do we do that in software as opposed to doing that on an ASIC or an FPGA? Those are some of the work that is going on. The soft-based RAN is essentially the software-based radio access. Prototyping for network slicing, vertical solutions. And then on the mobile edge communications, we've built technologies to develop edge-based solutions, whether we talk about having a platform with an SDK with an API so that you can build mobile edge computing applications very easily on a general purpose platforms. So typically speaking, historically, we look at the network with as 4 different categories of workloads. For ease of understanding, we look at the application level, control level, the packet processing, and the signal processing. Those are the 4 broad categories of workloads that we see within the network. And over time, what we've been trying to do at Intel is try to address more of these workloads on a general purpose platform so that it becomes easier to develop, easier to maintain and develop and deploy these type of workloads on a general purpose platform. And we do that using virtualized network applications where you have the general purpose platforms, and we build the applications on top of that. And we use the orchestration and the SDN controllers to build these type of different classes and categories of nodes. So I was reminded I'm out of time, but quickly I would want to summarize with something like this. So far the networks that have been built in a very vertical fashion, and they have been very static and purpose built. And we don't think that it fully comprehends the use cases that are going to come in the next few years down the road. And to be able to comprehend that, we need new standards. There is a lot of work happening in 3GPP, a lot of work happening in different industry bodies, as well as evolution of the roadmaps of how the networks are deployed. And we think that the SDN NFV technology is critical to the core as well as the access network to deliver on this promise of 5G. And along with that, whether we look at the enhancements at the silicon or the platform level or simplification of the network, these are very critical ingredients to go make the deliver on the promise of 5G. And lastly, one thing that I want to note is there are many usages of 5G that will come that we haven't even thought about. And that is exactly the reason why we need a platform which is open, which can be configured, which can be innovated on top of. And that's why we think SDN and NFV are extremely critical to enabling of 5G. So with that, thank you.
네. 영어 강의라고 제가 미리 설명을 안 드렸는데 여러분들 다 적응하셨을 거라고 제가 생각이 들고요. 오늘은 어떻게 이렇게 약간 글로벌 행사가 돼가지고 이따가 뒤에도 페이스북에서 오신 분도 영어로 강의를 해주실 예정입니다. 네, 그러면 일단 시간 관계상 바로 다음 세션으로 진행을 해보겠습니다. 다음은 아토리서치의 송용주 연구소장님을 모시고 텔코 인프라 분야의 벤처 경험담이라는 흥미로운 어떤 주제의 강연을 들어보도록 하겠습니다. 여러분 큰 박수로 환영해 주시기 바랍니다.